Welcome to part 2 of chapter 1. Last time was our very first lecture of the entire course, which is pretty exciting. And we looked at what chemistry is, what chemistry studies. We talked a bit about the scientific method, and then we started looking at how the periodic table is the world's greatest cheat sheet, right? We looked at metals, nonmetals, and metalloids. We talked about groups versus periods, and we started to talk a little bit about how the atoms or the elements were arranged on the periodic table. So today we are going to jump more into how the elements are arranged, and we're also going to talk a little bit about the history of the atom. So lots of good stuff to cover today, so let's go ahead and get started. So we're going to start off with some history of the atom. Don't worry, this is not a history class, so I'm just going to give you a very brief overview of the history of the atom because it's important to understand how we got to where we are today, because the research kind of continued to build on itself as we went. So early models of the atom were developed by the Greeks. Okay, they're the ones that did a lot of our initial kind of scientific thinking. And Empedocles proposed that matter was composed of 4 basic elements: earth, air, water, and fire. So I want to point out this word elements. This is not the same kind of elements that we are talking about in this class. Remember, elements are the ones that we talk about on the periodic table. If you look at the periodic table, water is not on there, right? Water is H2O. It's made up of hydrogen and oxygen. Similarly, earth, air, and fire, not on the periodic table. So just be really careful here. When we're talking about this term elements, it's a different kind of elements than we typically talk about in chemistry. So Democritus proposed that matter was composed of small, indivisible particles that he called atoms. Okay, so essentially Democritus said, all right, let's say we take a piece of paper and we tear it in half. And then we tear it in half again, and we tear it in half again, and we keep tearing up this piece of paper. Eventually, we would get to a point where, we couldn't tear it up anymore. There would be some fundamental particle that couldn't be divided. And this whole can't be divided, indivisible in Greek is atomos. So he said there's an atom, essentially, that's in there that we can't tear into pieces, which turns out to be right. He said these atoms could combine in different ways and give rise to a bunch of different compounds that we observe. All of this is true. So this was a long time ago, okay? And he was essentially kind of right. But the fact that Empedocles was friends with Aristotle, you guys have likely heard of Aristotle. He's an influential philosopher back in the Greek days, right? A long time ago. And Aristotle agreed with or supported Empedocles' theory, and so it wasn't until 2,000 years later. Isn't that nuts? This guy was right, Democritus, right? He was on the right track of, discovering the atom and all of these different things about it, but essentially all of the scientific progress stopped right there until 2,000 years later because Aristotle liked Empedocles' idea better, and Aristotle was popular. I think that kind of trend is mirrored in a lot of today's society, right? Where the, more popular people, their ideas are supported, even if they may not be correct, which is kind of interesting. But not going to get into that in this class. All right, so let's go back to the atom. So John Dalton, so again, flash forward 2,000 years from where Democritus left off. He said, all right, there's eventually, if we keep tearing up this piece of paper, there's going to be something so small that we can't tear it up anymore. John Dalton devised a theory to explain a lot of these observations that we were seeing in the 18th century. Okay? He said that matter is composed of tiny, indivisible particles called atoms. And that should make you think, hang on, wait, that's what this other guy said. Democritus proposed that matter was composed of small, indivisible particles he called atoms. And you're right. Democritus has the idea first, but he doesn't really do much with it because it wasn't the popular theory. So John Dalton was like, hey, all right, let's go back to this. If matter is composed of tiny, indivisible particles called atoms, then let's say all of these atoms that make up a given element are identical. right? So if you have a gold ring, all of those atoms of gold that are in your gold ring are going to be identical. And he said that, okay, the atoms of gold are going to be different from atoms of helium, right? Which makes sense, right? There's no helium in your gold ring because that's made up of helium atoms versus gold atoms and so on. So he said, all right, all gold atoms, they're the same, but gold atoms are different from helium atoms. And so a lot of what John Dalton said was true. Elements, for the most part, right, these tiny indivisible particles called atoms, for the most part, that's true. Matter is composed of tiny, tiny particles that are called atoms, but they're actually not indivisible, which means that there are things that are smaller than the atom. We know that there are protons, neutrons, and electrons in the atom now, right? He didn't then, but we know that now. Also, we can actually decompose our atoms. We can break atoms apart, which is kind of crazy, and that is nuclear chemistry. So if you know anything about nuclear power plants, that's actually how they work. They actually split atoms, which is why it releases so much energy. More on that actually in a different class. The other thing that he wasn't quite right about, not all atoms of the same element are identical. So atoms, even though they may both be gold atoms, they can actually have different masses. They can still both be gold, but they can have different masses. And these are called isotopes, which we will talk about later in this lecture. And like I said, atoms, they're not indivisible. They are composed of small subatomic particles. And these are protons, neutrons, and electrons, which we will get into more in this lecture. So the reason I'm pointing out all of these things about John Dalton is because he was on the right track. He had some really, really good ideas. They're not quite right, but they provided a really good foundation for us to learn more about how the atom is actually organized. So flash forward a bit more, by the end of the 1880s, right? He was in the early 1800s, now we're in the 1880s. A lot of the scientists were doing experiments with electricity. And they were starting to show that the atoms were composed of tiny particles that were called subatomic particles, like I said, protons, neutrons, and electrons. When you hear this term subatomic, sub just means smaller than the atom, okay? So our atoms are composed of protons, neutrons, and electrons. And it was shown that some of these particles, these protons, neutrons, electrons, some of them have a charge, okay? And so they started exploring more about these different charges and how these charges were arranged in the atom. But let's take a brief digression and we'll talk about charge in general. Charges, if you haven't had physics or anything else to do with electricity, two different types of charges. Charges can either be positive or negative. And so if it's positive, we denote that with a plus sign. And if it's negative, then we'll denote that with a minus sign. Opposite charges attract. You've likely heard in life opposites attract. That's true in chemistry. Positives and negatives will attract each other. Whereas like charges, if you have two positives or two negatives, they will repel each other. All right, so we needed to know that before we can go and talk about these experiments. So like I said, they were doing some experiments with electricity and also some experiments also with radiation. And one of the experiments or multiple experiments actually used these cathode ray tubes. And I don't need you to know a lot about these cathode ray tubes. I'm just going to use it to explain how we knew there was charged stuff in the atom, essentially. But the way it works is that we send this beam through, okay, and the beam can either be positively or negatively charged. We're going to send a beam of either positive or negative stuff through this tube. And this tube has had all of the air sucked out of it. So there's literally nothing in there, not even air. So we'll send this ray through it, and it will, we have two charged plates. We have a charge up here and a charge up here, and you'll see that they are opposites. So this one is negative and this one is positive. And we can use those plates to figure out whether this beam is positively charged or negatively charged. If it's attracted, like this one, A, up here, if it's attracted to the negative side, then it's going to be positively charged. But if it's attracted to the positive side, it's going to be negatively charged because, again, opposites attract, right? So positively charged beams will go up and then negatively charged beams would go down. So why is this all important? All right. J.J. Thomson. He's our next important fellow. So we talked about Democritus, John Dalton. Now we're on to J.J. Thomson. Okay, these are people that I would like you to remember. So J.J. Thomson, he noticed that the rays were being repelled by a plate bearing a negative charge, and they were being attracted to a plate bearing a positive charge. Okay, so the rays repelled by a negative charge, attracted to a positive charge. So, okay, these cathode rays then must be negatively charged. They're being repelled by a negative, attracted to a positive. So these cathode rays were actually negatively charged particles called electrons. So J.J. Thomson, what I want you to know about him is that J.J. Thomson discovered the electrons using cathode rays. Okay? Essentially, what all of this proved is that there are electrons in the atom. These cathode rays were coming out of the atom based on these, the radiation they were studying. So the cathode rays are coming from the atom and they are negatively charged. So there must be negatively charged stuff in our atom for it to be able to give off negatively charged stuff, right? So Dalton's theory of the atom had to be revised. Essentially, what Dalton had said is that atoms are solid, right? This is an atom, just like that, big atom. Okay, and what J.J. Thomson found is that nope, the atom has negative stuff in it. Not sure where it is, but there's definitely negative stuff in there. So we need to change our theory of the atom. So J.J. Thomson said, all right, there are negative stuff in the atom, but we know the atom as a whole is neutral. So if the whole atom is neutral, and we know there's negative stuff in there, that means there also has to be positive stuff to balance out these charges. Okay, so this is known as the plum pudding model. Essentially what it comes down to, this is our plum pudding model here. The yellow stuff that you see is all positively charged. That would be like our pudding, okay, if you're British. And then the negatively charged stuff is kind of spread throughout, and he made those as particles because of what they knew about these beams. You can also think about it as, as plum pudding. We're not British, and likely no one has eaten plum pudding. It is called the plum pudding model, but you can think about it as like a chocolate chip cookie model. All of the cookie would be our positively charged stuff, and our chips would be our negatively charged stuff. So here's our chocolate chips in our chocolate chip cookie. So you can think about it as like a chocolate chip cookie model. The cookie is positively charged and the chips are negatively charged. But like I said, called the plum pudding model. So that is the new model of the atom. No more John Dalton model with just that solid sphere. Now we have J.J. Thomson's model with incorporating those negatively charged particles. All right, flash forward a bit more. More people studying the atom. The next one that's really important, though, is Ernest Rutherford. Okay, he is credited with discovering the nuclear model of the atom. Okay, J.J. Thomson, plum pudding model. Rutherford studied the nuclear model. Okay, and let's talk more about his experiment. So he was using not cathode rays anymore, but he was using alpha particles. And these alpha particles are positively charged. Okay, so he used a bunch of positively charged alpha particles and shot them at a piece of foil. Okay, and so when he shot them at a piece of foil, he noticed that most of them went through. Most of them are not deflected. They went straight through. So they went straight through the foil because they are super small and positively charged. They went just right through. Some of them bounced off at these kind of like weird angles like this. And some of them actually bounced back, which is kind of crazy. So the ones that bounced back, he was like, whoa, I shot these alpha particles at this piece of gold foil. And instead of going through like they should, some of them bounced back. What are they hitting? There's something in there that they're hitting. These are hitting it too, right? What are all of these alpha particles? What are they hitting that's in there? So he said, okay, there must be something that's in the middle that it's hitting, like these little pieces, right? There must be something, or sorry, not those, my apologies. There must be something in the middle of this gold atom that it's hitting. What we thought before is that there were just these electrons scattered throughout the atom. And so if they were electrons, those are negatively charged. And so we just, the alpha particles, they were just going to go right through. That was what he predicted to happen. But what really happened is that instead of going right through, there was something in the middle that's hitting it and bouncing off. Okay, so he said, okay, there's this thing in the middle, and it must be really, really solid and dense, right, for it to be able to hit it. And it's not attracted to it. So it can't be an electron because I'm shooting, all of these beams that I'm shooting, these are positively charged beams. And if that was negatively charged in the middle there, it should stick to it because opposites attract. But it's not. It's going and it's bouncing off of it, right? Or it's being deflected by it. So it's not attracted to it, it's actually being repelled by it. So that means that this thing in the middle must be positively charged. Okay, so he said that something in the atom is very, very dense and it's positively charged, which is making all of these alpha particles bounce back. So Rutherford had to take all of this information into account and actually change the model of the atom again. Remember, the one that we had recently was J.J. Thomson's model, that kind of chocolate chip cookie model that said the electrons are spread out, which is still true. But the thing that needed to get added is that there's something very, very small and dense in the middle of the atom. We know it's really, really small because most of the atom was empty space. Remember, most of those alpha particles went straight through. Okay, like if we look back here, most of them were going all the way straight through. Very few of them were deflected. So most of it was actually empty space. But there's something really, really hard and small and dense in the middle of the atom. Okay, so he said that those protons, the positively charged things, that's going to be in the middle. It's going to be very small, very, very dense. Neutrons were also discovered around this time, and they are also going to end up in the middle. We're actually not going to talk about that, but the neutrons, they will end up in the middle as well. So then what about those electrons that J.J. Thomson discovered? If most of the atom is empty space, where are the electrons at? Well, the electrons are dispersed throughout the remainder of the atom. So those are these out here. So as you can see in this big, huge atom, most of it is just kind of nothing. It's just empty. And then we have very, very tiny electrons that are kind of scattered throughout. So the other thing that's really important, though, remember, they already knew that the atom was neutral. Okay, so if the atom is neutral, then the number of electrons that are negative must equal the number of protons that are positive to make this all balance out. So that's really important. Okay, neutral atoms contain the same number of protons and electrons so that the charge balance out, and this is neutral. Okay, so this is the nuclear model of the atom. Again, the nuclear model of the atom was discovered by Rutherford. Okay, all right, I know that was a lot of information. So we are going to pause here for a brain break and work on some problems. So find that chapter 1 lecture worksheet that you were working on last time. Pause here, do numbers 11 through 15 on your chapter 1 lecture worksheet, and then come back when you're ready to move forward. Alrighty. So we've been talking about these subatomic particles, right? Things that are smaller than the atom and contained within the atom. So protons were discovered by Rutherford. Remember, they are positively charged particles and they are found in the nucleus. Okay, the nucleus is that thing right in the middle of the atom that we said had all of the protons and the neutrons. Okay, if you look at this, we'll kind of look at this here for a second. Look at that atom. Do you see how small that nucleus is? Like, it's teeny, 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 tiny. I actually have a video that's linked in Canvas to talk about how small the nucleus really is. I think it relates it to a golf ball in the middle of a football stadium. Like, think about that for a minute. A golf ball sitting in the middle of a football stadium. That is how small the nucleus is compared to the rest of the atom. So it's really, really, really tiny. But all of those protons are jammed into that tiny, 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 tiny space. The neutrons are in there as well. They are actually neutral. Protons are positive, Neutrons are neutral particles, and they are also found in the nucleus. They are very, very slightly bigger than protons, but essentially we are going to say they are about the same size. Okay, so protons and neutrons found in the nucleus, which is in the middle of the atom. Electrons are negatively charged, and they are around the nucleus. Okay, so again, if we look at this kind of picture here, you don't actually see the electrons. The reason for this is that electrons are way smaller than protons and neutrons. And you may be looking at this thinking, well, protons and neutrons look pretty darn small to me. They are. And electrons are even smaller. Okay, so these teeny, teeny, tiny electrons are kind of floating around out here. Remember, like we said before, the atom is mostly empty space. Teeny, tiny nucleus in the middle, even smaller electrons around the outside, and mostly empty space. So, rather than continuing to write protons, neutrons, electrons a million times in your notes, we have some abbreviations that you are more than welcome to use. So electrons, we use E minus. Protons, and this is from your book, but protons are usually P plus, and neutrons are N0. Okay, and those are the symbols you can use to mean protons, neutrons, electrons. And then their relative charge. So electrons are negatively charged, protons are positively charged, and neutrons are neutral. And then we have their actual mass in grams over here to the right. We are actually not going to use that in this class, so you don't need to worry about that. But you can look at it, and you can see that electrons are very, very, very small, quite a bit smaller than our protons and neutrons, which are also pretty tiny. All right, so let's go ahead and do a practice problem. So the following table contains data sets that indicate numbers of subatomic particles. Which of the data sets represents neutral atoms? Okay, so remember, to be a neutral atom, the number of protons must equal the number of electrons in order to make this atom neutral. Okay, so I want you to tell me which sets of data represent neutral atoms. And I want you also, for those that do not represent neutral atoms, so the ones that are not neutral, figure out what the overall charge is. If it's not neutral, is it positively charged or is it negatively charged, based on the number of subatomic particles? So go ahead, pause here, come back when you're ready to see the answers. Alrighty, so the ones that are neutral are A and C. So if we look, our protons and our electrons have to be equal in order for it to be neutral. We do not care for the charge. We don't care about the neutrons at all. The neutrons can do whatever they want to do, and they're not going to affect our charge. We're only looking at the protons and the electrons. So that takes care of A and C. So looking at B and D, right, because they are the ones that are not neutral. So B versus D, B, we have 12 protons and 10 electrons. So looking at that, do you see that there are 2 extra protons? So since there are 2 extra protons, our charge is +2 because we have 2 protons that are not being balanced out. We have 2 extra protons, so we have 2 extra positive charges, which means it's a +2. If we look at D, we have 17 protons and 18 electrons. We have 1 extra electron. So since we have 1 extra electron, our charge is -1. Okay. Alrighty. So to sum up everything, we have protons and neutrons. They are in the tiny, tiny, tiny positively charged nucleus. Okay, again, tiny, tiny, tiny positively charged nucleus. And even though it's really small, that will make up most of the mass of the atom. Okay, protons and neutrons, like I said before, are much bigger than electrons. So the fact that most, the protons and the neutrons exist in the nucleus, that's where all of the mass goes. So when you hear about the nucleus, I want you to think, oh, that's where all the mass is. The protons and the neutrons make up all of the mass. Okay, and again, if the atom were the size of a football field, the nucleus is the size of a golf ball in the middle, which is crazy to me. All right, so the negatively charged electrons are not in the nucleus. They are super small and have a super small mass, but they occupy all of the space in the nucleus. So when you think about electrons, okay, I want you to think about the volume of space. They take up all the space, right? Even though the electrons are small, they're in that outside part that's not the nucleus. So that's where all of the space is, on the outside. Okay. Our chemical properties of the atoms, so essentially the study of chemistry, is based on the number of protons, neutrons, and electrons. So everything that we are going to study is based on the numbers of protons, neutrons, electrons. And if you change those, then you're going to change how that element reacts. Okay. There are actually more subatomic particles that are known now. There are quarks and gluons and all kinds of things that sound made up. But all of that is going to be left for later chemistry classes. The theories of the atomic structure based on these 3 subatomic particles are all we need to do most chemistry, and especially the level of chemistry in this class. All right. Moving on to talk about atomic number. Okay, so hopefully you have that periodic table handy. Whenever you are watching a lecture of chemistry, or if you are working on the lecture worksheets or working on your homework, always have that periodic table handy, the one that we were making notes on last time and that you very lightly colored, because I'm going to refer to it as we go through these lectures. So you will see a number. Like if you look at hydrogen, there's a number 1 and helium has a number 2, right? That is the atomic number, okay? And the atomic number is telling you the number of protons in an atom. Usually, like if you look at your periodic table, it should look like this. It'll have like the number up top, and then it'll say hydrogen, and it'll have the mass, which is 1.008, and maybe some other numbers, right? But this number at the top, that is the atomic number. That's telling you the number of protons that are in the nucleus of the atom. The atomic number is really important because it tells you the identity of the atom. Anything that has 1 proton, always going to be hydrogen. If it has 2 protons, it's helium, right? If it has 3 protons, right? And so on and so forth. The number of protons tells you which atom it is, okay? So here's another example. If we look at cobalt, that atomic number is going to be on the top. Cobalt is atomic number 27. So that's telling you that cobalt has 27 protons. So our atomic number is always going to be the one on the top that's going to be above the element symbol. It's always going to be a whole number. So if you can't remember if it's on the top or the bottom, our atomic number is always a whole number. You have to have a whole number of protons. You're not having like 2.5 protons, right? You're always going to have a whole number. The cool thing is that because all of these elements are neutral, the number of electrons is going to be the same as the number of protons. So like for cobalt, we know it has 27 protons. It's also going to have 27 electrons. Because remember, in a neutral atom, the protons and electrons must be equal in order to cancel out and give the atom an overall neutral charge. So positives and negatives will be equal, so protons and electrons will be equal. So this atomic number is telling you the number of protons and electrons in a neutral atom, okay, which is super cool. And we're only going to work with neutral atoms right at this moment. All right, so like I said, the number of protons tells you what atom it is. So like if we had something with 11 protons, we know that's going to be sodium because its atomic number 11, and anything with 11 protons has to be sodium, okay? And I talked about this last time. The elements are arranged in order of atomic number, right? I told you this is going to be the world's greatest cheat sheet. So Mendeleev, the father of the modern periodic table, he put these in order of increasing atomic number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Very, very cool. But they're arranged by increasing atomic number. A common question on quizzes and tests is I ask how the elements are arranged. Is it by atomic number or atomic mass? And you will need to remember it's arranged by atomic number. A lot of times it will also, like the mass kind of increases as well, but there are some exceptions to this. And it might be fun for you to check out your periodic table and see if you can find any exceptions to this rule. It is actually a question on one of our labs that will be coming up shortly as well. So they're arranged in order of increasing atomic number. All right, so I want you to do this practice problem, and you can just do it somewhere in your notes and complete this table. So calcium is our element. Fill in the chemical symbol. Okay, remember it's going to be 1 or 2 letters, that abbreviation. This will help you start memorizing them for the upcoming quiz. So fill in the chemical symbol and then fill in the atomic number for each one of these. So go ahead, pause here, do this, and then come back when you're ready to move forward. Alrighty, so calcium is Ca and its atomic number 20. Copper is Cu, okay, and its atomic number 29. And then aluminum is Al and its atomic number 13. So if you have any questions on this, go ahead and send them to me. Otherwise, we will move forward. All right, time to take a break and work on some problems on your lecture worksheet. So do numbers 16 through 18 on the Chapter 1 lecture worksheet, and then come back when you're ready to move forward. Alrighty, let's keep going. So after the discovery of the nuclear model of the atom, so after Rutherford did all of his work, the mass of almost all of these atoms was found to be larger than expected. So they added up the masses of the protons and the electrons, and they're like, okay, that's not equaling our mass. What is going on? That's how the neutrons were discovered. Okay, they said there has to be something else in there that has mass, but it's not positively charged or negatively charged, because we know the positives and the negatives are canceling out, right? The protons and the electrons are equal and are canceling out. So something in there has mass, but has no charge. So neutrons. All of our atoms of the same element, like we were talking about before, have the same number of protons. We get that from the atomic number, right? Carbon is number 12, therefore it has 12 protons. However, atoms of the same element can have different numbers of neutrons, because remember, the protons and the electrons, they have to equal out. And so they're always, carbon is always going to have 12 protons and 12 electrons if it's neutral. And the fact that it has 12 protons means it's carbon. The neutrons, because they're neutral, they don't have to be equal to anything. They're not identifying the atom, right? They can have varying numbers, which is kind of crazy. And so if they have different numbers of neutrons, that means they are going to have different masses. Okay, and so these atoms that have the same atomic number but a different mass, these are called isotopes. And I want you to know this term. Atoms of the same element, different numbers of neutrons, therefore a different mass. So for example, here are some isotopes of hydrogen. They all have 1 proton, okay? The number on the bottom, we'll talk about this in a minute, the number on the bottom is the atomic number. Do you see that that number is the same in each one of these pictures? The fact that that bottom number is the same, that's telling you they all have 1 proton, and therefore they're all hydrogen. The number on the top, that's the mass number. Do you see that the masses are different? So 1 versus 2 versus 3. That's because this one has 1 neutron and that one has 2 neutrons. So when we add neutrons, that's changing the mass. That's why that number on the top is different. The mass is changing because they have different numbers of neutrons. But they're all still hydrogen because they all have 1 proton. So the mass number that we're seeing on the top here, this number on the top, that mass number, that's the total number of neutrons and protons in an atomic nucleus. So let's say the first isotope of hydrogen, it had 1 proton, it had no neutrons, so 1 plus 0 gives us a mass number of 1. Whereas if we look at an isotope of chlorine, it has 17 protons, 20 neutrons, therefore its mass number is 37. So our mass number is the number of protons plus neutrons in the nucleus. Okay? Don't get that confused with atomic number that was telling us the number of protons and the number of electrons. Lots of different numbers happening here. All right, So I want to talk a little bit about this isotopic notation that you were seeing here, right? Where I was telling you that mass was on the top. So the number on the top is the mass number. Remember, that's the total number of protons and neutrons in the nucleus. That will always be the larger number. The number on the bottom is the atomic number. That's the number of protons in the nucleus. Okay, and then over there, we have our symbol of our element. Okay, so if you go and you look at, let's say, hydrogen, you find your periodic table and you see it's got a 1 on the top, it's got an H, and then it's got 1.008. Okay, when we write this in isotopic notation, we use our element symbol, that's H. Our atomic number, remember our atomic number is up here, that was our atomic number. When we write it in isotopic notation, our atomic number goes on the bottom. Okay, so instead of it was on the top, now it's on the bottom. This down here is not the mass number. Okay, the mass number is always a whole number. That number on the bottom is the atomic mass. And I know that's kind of confusing. They sound really similar, right? This is the atomic mass. And the way that we get the mass number is we just round this to a whole number. So that's 1.008. If we round that to a whole number, that makes it 1. So that's what would go on the top here. Okay, so the mass number is the atomic mass rounded to the nearest whole number. So like if you looked at carbon, carbon is atomic number 6, and it has a mass of 12.0011, I believe. And so when we write this, we would have carbon, we would put the 6 on the bottom, that's telling us it has 6 protons, and then that 12 is going to go on the top. Okay, remember, we're going to take that atomic mass and we are going to round it to the nearest whole number. Okay, so all of these, when you write them in isotopic notation, should always have whole numbers, no decimals. So when we write our elements, right, like this, in our isotopic notation, it's actually really well set up for figuring out the number of neutrons. Remember, the number of neutrons can change in different isotopes of an element. So like if we look at hydrogen here, the way that this is set up, remember, the mass number is on the top and the atomic number is on the bottom. So we can actually just do subtraction straight down to figure out the number of neutrons. So we do our 1 minus our 1, which is shown below, and that gets us 0 neutrons. Hydrogen, actually, fun fact, is the only element that has 0 neutrons, which is kind of cool. If we look at oxygen to figure out the number of neutrons, again, it's set up for subtraction. The mass is on the top, the atomic number is on the bottom, and we can just subtract them, and we can get that there are 8 neutrons in this particular isotope. And then, you know, you can do that for anything, as long as it's set up with the mass number on the top, atomic number on the bottom. So that's how you can remember which one goes on the top or on the bottom. Remember, it needs to be set up for subtraction to figure out the number of neutrons. All right, so looking at this, this says how many protons, neutrons, and electrons are found in the following isotope. Okay, so looking at this, Cu, just in case, or just a quick reminder, you're supposed to be memorizing those symbols that go with the names. Cu is copper. Okay, so using this information shown here, how many protons, neutrons, and electrons are found in this isotope of copper? So go ahead, pause here, try and figure that out, come back when you're ready to see the answer. Alrighty, so going through this, the number on the bottom, remember, that is our atomic number. So that is going to tell us how many protons there are. Since there are 29 protons, there also have to be 29 electrons because the positives and the negatives have to be equal. So 29 protons, therefore also 29 electrons. So the only thing we need to figure out now is our number of neutrons. The way that we figure out the neutrons is through this little formula. We do our mass number minus our atomic number. Okay, and so remember, this is set up for subtraction. We can do 64 minus 29, and that will get us our number of neutrons. So there are 35 neutrons in this isotope of copper. Here's another one. Which isotope corresponds to an element with 24 protons and 28 neutrons? So go ahead, pause here, come back when you're ready to see the answer. All right, so the way that we figure this out is we will use this 24 protons to figure out what element symbol it is. Remember, the fact that we have 24 protons, that tells us our atomic number. So that is going to be the number on the bottom. So this one doesn't have a 24 on the bottom, so that's out. That one doesn't have a 24 on the bottom. That one doesn't have a 24 on the bottom. That one doesn't have a 24 on the bottom. So even just if you got that far, the only one that has a 24 on the bottom in the correct place for the atomic number is B. But let's go through this anyways. So that 24 protons, right, again, that 24 has to be on the bottom, and that's telling us, if we look up atomic number 24, you will see that that's chromium, okay? And so to figure out the number on the top, we do 24 plus 28, and that will get us 52. So that is the number that's on the top there, okay? Alrighty. So let's think about this. What happens if you change the number of protons in an atom? So remember, if we change the number of protons in an atom, it becomes a different element. Remember, the number of protons tells us the atomic number. So if it has, 2 protons, that means it's helium. If it only has 1 proton, that means it's hydrogen. Okay, the number of protons tells us which atom it is. If we change the number of protons, then we change it to a different element. All right, let's try another one. What happens if you change the number of neutrons in an atom? So if we change the number of neutrons, it just becomes a different isotope, right? That means it's going to have a different mass. It's still going to be the same element. It still might be carbon, but instead of being carbon with a mass of 12, maybe it's carbon with a mass of 13 or carbon with a mass of 14. Changing the number of neutrons just changes the mass, which makes it a different isotope. All right, what happens if we change the number of electrons in an atom? So if we change the number of electrons, then our electrons and our protons won't be equal anymore. So that's going to change the charge of the atom. It won't be neutral anymore. So let's try another one. What is wrong with this? So when we're looking at what's wrong with this, the fact that this is number 11, that is not magnesium. Magnesium is number 12, okay? So it's the wrong element symbol here. Alrighty, now we're going to pause here and complete problems number 19 through 30 on the Chapter 1 lecture worksheet to work on all of this stuff with protons, neutrons, electrons, mass number, atomic number, all of that good stuff. So get really good at that, and we have a bit more to cover in Chapter 1 when you're ready to come back. Alrighty, remember we were talking a little bit about the atomic mass earlier, and I keep using this example where we have the 1 and hydrogen and then the 1.008. Okay, so that mass is not a whole number, right? That atomic mass is different from the mass number. So in this section, we're going to talk about what the atomic mass is and why it's not a whole number, okay? So the mass of a single atom. So let's think about an atom, right? I told you atoms are really, really small. So the mass of a single atom is so small, we can't see it with the naked eye. So that mass is not useful to be reported in grams. right? Grams, and I know in the United States we don't use a lot of grams, we more use ounces and pounds and things like that. But the scales in the back of our labs will measure things in grams. So like you could put your pencil on the scale and it would tell you some number of grams. We use grams for things that we can hold and carry around. But atoms are so small we can't see them with the naked eye, so it doesn't make sense to talk about their mass in grams because they are so small. So instead, we use relative atomic mass units, or this AMU as it's abbreviated. Most of everything we study in most of everything we study in chemistry is based on the carbon atom. So here is the carbon atom we will base everything on. Carbon-12 is the most common isotope of carbon. So carbon has an atomic number of 6 and a mass number of 12. And so they said one atomic mass unit is equal to 1/12 the mass of carbon-12. So that's the definition of an AMU. And if we were to convert between AMUs and grams, you would see it's 1.6606 times 10 to the minus 24th grams. That's really small, right? So AMUs are used to talk about the mass of things that are very, 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 very tiny. So all of those masses on the periodic table are measured in AMUs. You'll notice it doesn't have a unit. We'll talk about why a little bit later. But all of those, if we think about that mass number or that atomic mass that's on the bottom in AMUs, that's telling you the mass of one atom of that element. And all of those masses are based on the carbon-12 isotope. So a proton has a mass of about 1.007 AMUs, and a neutron has a mass about 1.008 AMUs. So like I told you before, they're about the same size, with the neutron being just ever so slightly bigger. But for all intents and purposes, essentially the same size. An electron, though, has a very, 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 very tiny mass. Much smaller than protons and neutrons. So if you'll remember, we said most of the mass of the atom was contained in the nucleus because that's where the protons and the neutrons are. So these two make up most of the mass of the atom in the nucleus. And essentially, we say that the electrons have kind of like no mass because they are so small. In reality, they do have a little bit of mass, but the way I think about this is, let's say you were standing on the scale. In your house, and 2 hairs fell off your head. Did that change the mass that it was showing on the scale? No, because the hairs on your head are so small, right? You can think about the hairs on your head as being an electron. They're there, they have some mass, right? But it's so small it doesn't really change the mass of the atom. So if you'll recall earlier, I talked about the fact that the atomic mass on the periodic table is not a whole number. This is because we need a way to reflect all of the different isotopes of that element into that atomic mass. For example, we talked earlier about sulfur. Sulfur is this yellow nonmetal powder that's kind of smelly, right? But there are a bunch of different isotopes of sulfur that are out there. So if you think about sulfur, sulfur can have a mass of 32, 33, 34, or 36. When you're looking at these isotopes, you'll notice there's no number on the bottom. That's because anytime we say that it's sulfur, it's always going to have the same number of protons. So that number that's on the bottom can actually be left out. The number that's on the top is the one that's really important because that is telling us the mass number, which helps us know which isotope of sulfur we're dealing with. But if you look at their percent abundances, this percent abundance tells you how likely you are to find that particular isotope of sulfur out in nature. Do you see that you're most likely to find isotope with a mass of 32, whereas the mass of 36 is really uncommon? So when we're looking at the atomic mass on the periodic table, the reason it's not a whole number is because it takes all of these different isotopes and their percent abundances, and we calculate this average atomic mass for sulfur. So all of the isotopes, or all of the elements pretty much, have different mixtures of isotopes. And so that atomic mass on the bottom is a weighted average, okay? It's not a normal average. It's not like, okay, add them all up and divide by 4, right? That wouldn't work because it's more common that you're going to find an isotope with a mass of 32 than it is that you're going to find a mass with 36. So we have what's called a weighted average of all the naturally occurring isotopes of the element. So I'll show you how to calculate that. For example, copper exists as two major isotopes. We have copper 63 and copper 65. Okay, the way that we get this mass of copper on the periodic table is we are going to take the percentage abundances and incorporate them into an equation, and it will equal this. Okay, copper 63 is more abundant than copper 65, so the mass on our periodic table that we're seeing is closer to copper 63 than it is to copper 65 because of this calculation, okay, because of this weighted average. And I do want to remind you again, the atomic mass is not the same as the mass number. The atomic mass is this, right? That is always going to be a decimal number. So our atomic mass is going to be a decimal number, whereas our mass number is always going to be a whole number because it's the number of protons plus neutrons. So please, please, please keep those straight. All right, so like I said, most elements are going to have two or more isotopes that contribute to the atomic mass of that element. So like lithium has lithium-6 and lithium-7. Do you see that this atomic mass is closer to 7 than it is to 6? That means that the one with the mass, the isotope with the mass of 7 is more abundant. It's more commonly found in nature because our atomic mass is closer to 7. Same thing with carbon, right? Do you see that's almost 12? That means the most common isotope of carbon is 12, and isotopes with a mass of 13 and 14 are less common. Okay. All right, so let's figure out how do we do this calculation. Okay, so the way that you're going to do it is you're going to take your atomic mass times its percent abundance as a decimal. Okay, so you'll see here it's 69.09%. The way that you make that a decimal is you just divide it by 100. Okay, so both of these divide by 100. So you'll take your mass times your percent abundance, right? There's our mass, there's our percent abundance. And then you're going to add it to the next one, the mass times the percent abundance. Okay, and you're going to do that for however many isotopes you have. There are 2 isotopes of copper, so we're just going to do that twice. If there were 3, we would do this 3 times. If there's 4, we do it 4 times, right? But it's always going to be mass times percent abundance, mass times percent abundance, and you're just going to add them all up. So let's do another one. Silver exists as 2 isotopes with atomic masses of 106.9041 and 108.9047 AMU. And we want to figure out the average atomic mass for silver. Okay, so the percent abundances for each isotope is 51.82 and 48.18% respectively. And when it says respectively, if you're not familiar with that, that means that this first number goes with the first number and the second number goes with the second number. So again, we're going to do mass times percent, and add them all up. So here we have our mass times our percent. And remember, we need to use our percent as a decimal. So we're going to divide it by 100. So our mass times our percent. Okay, and then we'll do the next one. Mass times percent. So we'll take our mass times percent. And once you do those calculations, add them up, you'll get your AMUs. I do want to point out, when you are doing these types of calculations, I would recommend punch this in your calculator first. Mass times percent. And then punch this in your calculator. Mass times percent. And then write each of those numbers down and then add them together at the end. Okay, I would not try and put this whole thing in your calculator all at once. You totally can. It's going to require you to use lots of parentheses, but I have just found that sometimes people will do them wrong. They'll forget a parenthesis, or they'll have too many, they'll get an error message. So I would do this calculation, press equals, write that number down, do this calculation, press equals, write that number down, and then add them together to get your answer. Okay, but again, always mass times percent, mass times percent. Alrighty, one last practice problem. So this one is a little bit different. We're going to solve for one of the masses of our isotope. So chlorine exists as two different isotopes, chlorine 35 and chlorine 37. And it gave us the mass there of chlorine 37. If the percent abundance of each isotope is 75.53 and 24.47% respectively, what is the average? And the average atomic mass of chlorine is 35.46 AMUs. What is the mass of chlorine 35? So this is a little bit different. It gave us the average atomic mass, the one that we were solving for in the last couple problems. And it wants to know instead, what is the mass of one of the isotopes? Okay. So what I would recommend doing is plug everything in. We know it goes mass times percent, mass times percent, mass times percent, and then add them all up, right? So we don't know the mass of this one. So I'm just going to put A, just to have some letter. You can put X, you could put M for mass, you can put whatever you want. I just put A because it's the first of our isotopes. So mass that we don't know times our percent, and remember, our percent needs to be as a decimal. And then we're gonna take our second mass times the second percent. Okay, and then we already have our average atomic mass. So we're going to fill that in there. So now this just requires a little bit of algebra. Okay, so we'll multiply these two numbers together, and when we multiply these two numbers together, we get 9.046. Okay, so we'll subtract that from each side. So we'll go minus 9.046 from both sides. And that will get us what you see down there. And then we'll divide both sides by 0.7553. And that will get us our answer. Okay, so you can use this whole mass times percent. You can use that to figure out the mass of one of the isotopes as well. But just fill everything in and solve using algebra. Alrighty, I know that was a long lecture with a lot of information, but you've made it. You've made it to the end. Now what I want you to do is work on problems number 31 through 37 on the Chapter 1 lecture worksheet. So that should allow you to completely finish all of the Chapter 1 lecture worksheet. Once you're done with that, obviously send me any questions you have. I like to answer questions. But once you're done with that, then I would recommend working on that Chapter 1 homework assignment that's been assigned online. Remember, that's worth points. These lecture worksheets are not worth any points. They are just for you to practice and learn how to do things. Okay? Remember, the answer key is available on Canvas. So while you're working, check your answers. Make sure you're doing them right. Okay? What I would recommend is, be working on it and maybe have that answer key up so you can continually check your answers as you go. Once you've done the entire lecture worksheet and you feel really confident about all of your answers, you don't have any more questions, then I would recommend going and working on that homework assignment because that's what's worth points. If along the way you ever have any questions, whether it's watching the lecture, working on lecture worksheets, working on your homework assignments, please feel free to reach out to me and ask me questions. Remember, I like to answer questions. That's why I teach chemistry, and I'm here to help you. I'm on your side. I want you to be successful. So if you have any questions, please, 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 please reach out, and I'm more than happy to help you. Otherwise, keep working really hard, and I will talk to you guys next time.